Now we know that sometimes we draw a curve and we can draw a line that cuts through it and intersects it at 2 points. Now what is the slope of that line? Well, that's the slope of a secant. A tangent would be contacts the curve only at 1 point and is of the same slope as a curve at that point. So an average rate of change, hey, we know that the rate of change, the slope of a curve, will vary, right? I mean, this is not an even curve. But hey, between this point and that point, what is the overall rate of change? The average rate of change? Well, that depends on delta x and delta y. The intervening lines don't matter. All we do is draw a straight line, find that thing's slope, which is going to be delta y over delta x. So rise over run. I mean, you can say run a 5-kilometer race in an hour if you so wish, if you take, say, breaks in between. So, but the average speed is still going to be, 5 kilometers were covered in 1 hour. The average speed is still going to be 5 kilometers an hour, assuming, of course, that you didn't backtrack or something, which would add to this. By the way, that's a complexity that will affect some of the examples we do. So here we launch an object from the top of a building. The equation below gives the distance of the object to the ground in meters over time in seconds. Find the average speed between t equals 1 and t equals 3. So here we have negative 5t squared plus 10. First of all, we're going to end up with some pretty ridiculous results with the object going underground, or at least under the reference level. Why? Well, we don't know if the ground is being used as a reference level or not. Usually it is, but not always. So unless otherwise specified, we won't assume that going underground is not doable. So t equals 0, y is, well, t is 0, so y is 10. T is 1, well, negative 5 times 1 plus 10 is 5. T equals 2, and we would get negative 10. T equals 3, negative 5 times 9 is minus 45. So minus 35 here. Now, the average speed between t equals 1 and t equals 3, we have to note that average speed and average velocity are not the same thing. Why? Oh, say I ran over there and then I ran back. Well, this is actually a bit of a physics issue. If you're familiar with grade 11 physics, displacements, you would know this. So I ran over there, I ran back. My average speed was some number that is not 0. My average velocity, though, well, where was I at the start? Position 0. Where am I at the end? Position 0. And the amount of time is not 0. So my average velocity was no change in position over time. 0. Whereas speed was not. Speed is distance over time. And in this case, because these distances we're using are actually displacements, otherwise we wouldn't have a negative direction involved, well, height is a displacement, as in above ground. Because these are displacements, what we actually want for speed is a positive value. We're not looking for, velocity is 5 meters per second up or 5 meters per second down. We're looking for speed, which doesn't have a direction. So what we're dealing with is speed will be positive, thus it has to be delta y So change in y over delta t, but this is the absolute value of the change in y. So y2, you can also write it this way if you particularly feel like. And this would give us, well, y2 is t equals 3, negative 35, minus y1, which is 5, over 3 minus 1. So this is going to be 40 over 2. So 20 meters per second. Now please note that the actual symbol here should be v average. If this was velocity, we'd have an arrow on top to denote that it is a vector. But this isn't. So what we're looking for is just not vector speed. Of course, we should really put a statement, but we'll omit that for time. All right, average rate of change. Let's launch another object from the top of a building. The equation below is the height of the object in meters over the time in seconds. Find the average speed between x equals 0 and x equals 3. Now, here we have x minus 2 squared. This does not imply that at this being less than 0, that the object was not in flight. So, at x equals 0, what do we have? Well, x minus 2 is going to be negative 2, and squared, 4, minus 5 times 4 is negative 20, and plus 20 is 0. So what about x equals 1? Well, negative 5 times 1 is negative 5, plus 20 is 15. What about 2? Well, this whole thing is 0, plus 20, 20. And then we start going back down. We pass the top of the parabola, and we get to this. 3. This is part of the complexity of a problem. Why? Because the actual change in height, the actual vertical speed, considers the distance, not your start position versus your end position. It's not quite as simple as displacement is. So 3, we're going to have 15 again, and 4, we're going to have 0 again. Distance covered from x equals 0 to x equals 3 is 20 meters up, then 5 meters down. Total 25 meters. So V average, here we can't use just y2 minus y1 because it's not that straightforward anymore. So this is 25 over 3 minus 0 equals 25 over 3. So 8 and 1/3. And this is in meters per second. So as we can see, sometimes these questions are not actually average rate of change questions per se. They aren't just from start to end. Because the rate of change we're dealing with could be velocity, in which case we just care about start and end positions. Fine. Or we could be dealing with speed, which is very different. This has to consider, oh, did I run around the racetrack? Or did I just stand here? For velocity, it doesn't matter if you run around the racetrack or just stand there, as long as you end up and start at the same point. You always have a velocity of 0 if you do that. At least 0 relative to the racetrack, or the ground that the racetrack sits on. Why? Because Earth moves. As Galileo supposedly said at a trial of his, by the way, the Pope actually supported heliocentrism due to sheer acknowledgement of reality. What the Pope didn't support so much was the fact that when he asked Galileo to write something for him, the character that the Pope was supposed to be represented by was described by Galileo as a baboon. I do not believe that any person of authority is going to be very pleased with a guy who wouldn't let other scientists use his telescopes for fear of them discovering something he didn't, get away with calling him a baboon without being at least like, hey, what are you doing? Come on, really? So, hence part of the problems they had with Galileo. But anyhow, supposedly during his trial, Galileo kicks the ground and said, muttered as he left, and it does move. And it does. So velocity is relative. Speed is also going to need references. Okay, so let's do one more example. We are going to do something that's slightly less, hey, what about if it goes up and then down for speed? Or how about running around a track versus standing there for speed? So here we have to deal with volume and surface area. We have a snowball that is melting. Now we see that the volume isn't going to grow and then shrink. So the average rate of change that we're dealing with is purely going to be start point, end point. So radius is initially 40 and then finally 30. And volume is initially 4 over 3 pi 40 cubed. This is equal to, well, 4 times 4 is 16. 16 squared, so 4 to the 4th power, is 256. 256, 0, 0, 0, over 3 pi. And what about this down here? 4 over 3 pi times 30 cubed. We're dealing with, well, okay. First, we can cancel out the 3, and this will go from 27,000 to 9,000, because 900 times 10. So 9,000 times 4 is 36,000 pi. Now, the surface area, we should make it clear that this is a table, just in case anybody didn't quite notice yet. So 4 pi r squared, that's 4 pi 40 squared. This is equal to 40 squared is 1600 times 4, we get 6400 pi. And 30, this is going to be 900 times 4. So 3600 pi. The delta symbol is what we use for change. So delta V is the change in volume. Delta V average, though, is equal to V2 minus V1, or just delta V, over T2 minus T1. But wait a second. We're not dealing with T. So what we should be using instead, this is the usual form if we're dealing with time. That would be, loss of however many cubic centimeters per second or per hour. But here we're doing cubic centimeters lost per centimeter of radius. So this is going to end up being a little bit more awkward. Now, how would that look? Delta V average, V2 minus V1 over R2 minus R1. Now this is what we're looking for here. Now, I mean, we could figure this out using other methods such as derivatives. But we're looking for an average rate of change, not instantaneous. So there is no point in going into calculus quite yet. Even though quite soon we'll end up dealing with things that very much approach calculus. So here we're dealing with V2 is this 36,000 pi minus 256,000 over 3 pi over R2 is 30 minus for R1 is 40. You'll notice that we will end up with a rate of change that ends up being positive. This is how much on average volume we would have gained if we went up from 30 to 40. So here 36,000 is equal to how many over 3? 108,000. So 108 minus 256, whatever. 108 minus 256, negative 148,000 over 3. Negative 8,000 over 3 pi over negative 10. So this is equal to 148. First of all, the negatives cancel, and also we can get rid of one of the zeros. 0, 0 over 3 pi. Now what are the units? The volume was in cubic centimeters. The radius, or radii rather, are in centimeters. So this is centimeters squared. Now this might sound really weird for change in volume. But, well, think about what volume is made of. Infinitely many layers of area make up the volume. Now, okay, that gets into integration, which we won't talk about for now until we get to calculus class. So for surface, we're dealing with from 6400 pi to 3600 pi. Or SA, depending on where you are. Average is equal to S2 minus S1 over R2 minus R1. So this is, once again, we reiterate that we're going from 40 centimeters to 30 centimeters and from 6400 pi to 3600 pi. 3600 pi minus 6400 pi over radius 2 is 30 minus radius 1, 40. So we're dealing with 64 minus 36, negative 2800 pi over negative 10. So this is equal to 280 pi. Now, what are the units? Centimeters squared for surface area divided by centimeters for radius. So this is in centimeters. I mean, you could write centimeters squared per centimeter, but hey. So you'll find that sometimes rates of change can have pretty interesting units when you're not using the conventional stuff like rate of change over time, which usually comes out to, meters cubed per second or something. That at least doesn't sound like, hey, the rate of change in surface area is in centimeters? Well, actually the explanation in greater detail requires calculus, which we aren't there yet. So that's it for this section, and hopefully we have gained a better appreciation for how calculating the rate of change between 2 points on a curve, the average rate of change, can be more complicated than just taking the slope of this thing, which is usually the way it's done. This works fine if you're talking about, say, velocity, but if you're talking about distance, what you're looking at for, say, this racetrack is going to be to the top and then to there. So 2 stretches. Consult your teacher carefully if the question isn't too clear on what you're specifically supposed to be calculating. Because just numbly approaching a question as if it is displacement, velocity, whatever, vector problems pretty much, doesn't necessarily end well. So, that's it for this section, and we'll see each other again then, next section.